So let me begin by just introducing and reintroducing and reviewing the concepts that we previously looked at. In the initial videos, we looked at the concept of a closed system. And for a closed system, we said that energy transfers are possible in terms of obviously the work done or the heat content that is being exchanged, but no mass is transferred in and out of the system. In my previous video, we started talking about the conservation of mass for a control volume. And when we talk about a control volume, that is basically an open system. So if this was a control volume, then um, basically energy changes obviously still take place, but mass can also be exchanged between the system and the surroundings. So that is one major difference. So control volume is also called an open system, and that is what we are looking at in the previous video and in this video as well. So in the previous video we talked about, let me just review what we talked about. We started talking about conservation of mass for a control volume, and let me just review that for you. That what it means is that the total mass that enters this control volume during a certain time and minus the total mass that leaves that control volume during the same time is going to be equal to the net change of mass within the control volume during that time. Okay, so that is simple enough. This is called the conservation of mass principle for a control volume. And in terms of an equation, this is how we represent it. In the last video, we saw that m dot in, we call this m dot I, incoming, and m dot out, we represented it as m dot E. So that is the exiting mass flow rate. Over here, this was the incoming mass flow rate. These are one and the same things. Don't get confused by the subscripts here. They just mean the same thing. And they're going to be equal to the net change of mass, which is going to be the derivative. So the net change of mass within the control volume during that same time. And the units we saw were kilogram per second. And then we saw a special case of this system when we talk about a steady flow. And with a steady flow, what we mean is that the mass within the control volume can change. It changes continuously, but the total mass amount remains constant within that control volume. So the total mass that is incoming into the system is going to be equal to total mass outgoing, because this goes out, this is equal to 0 because the mass remains constant, okay, for this special case, for a steady state control volume system. And just to give you an example of what this means is that if you were looking at a system with 2 inlets and 1 outlet, then the total mass flowing into the control volume, which is going to be m dot 1 in this case, plus m dot 2, this is going to be equal to the total mass that is going to be exiting the control volume. And the mass that is exiting out of the control volume is going to be represented by m dot 3 over here. So 2 kilogram per second and 3 kilogram per second is entering into this control volume. So obviously the mass that is going to be exiting out of the system is going to be equal to m dot 1 plus m dot 2, which is 5 kilograms per second. So the same amount of mass flows into the system and the same amount of mass exits the control volume as well. Okay, so that is one special case, which is called a steady flow system or a steady state system. So now to develop the concepts for a control volume further, I'm going to talk about conservation of energy for a control volume, and what that essentially means is conservation of energy principle that we've already looked at for a closed system, right? So what does conservation of energy mean? That energy is conserved. And we've applied it to a closed system previously, and now we're going to be applying it to a control volume. But before I do that, I'm just going to remind you of a couple of concepts that we've already studied. And one of those concepts was the total energy of a system. And the total energy of a simple compressible system that we saw was in terms of internal energy. And this is on a unit mass basis, so that's why it's being represented by small case letters. So it's composed of internal energy plus the kinetic energy, which can be written in terms of half v square, because obviously it's on a per unit basis, unit mass basis, so obviously m is equal to 1 here, the mass is equal to 1. So this is the kinetic energy part of it, and plus the potential energy, which is going to be equal to mg into z, but again, it's on a unit mass basis, so mass is going to be equal to 1, and this is going to give you the potential energy part of the total energy. So total energy of a simple compressible system is composed of internal energy, kinetic energy, and potential energy. And another concept that we discussed was in terms of, for a closed system, what we saw was that change in energy, E2 minus E1, is equal to heat content and work done across that system. Or we could write the left-hand side of this equation in terms of delta E, and this is going to be equal to, again, Q minus W. Q is the heat content, and W represents the work done. And we use the same notations that we already talked about. And if I was to divide the entire equation by delta T, and then take the limit across both sides when delta T approaches 0, so the left-hand side of the equation would become a derivative, which is going to be in the form of dE by dt. And the right-hand side of the equation, we know that derivatives can be written in terms of dot. So I could write this as q dot minus w dot, right? So this is what we saw for a closed system. This is applicable for a closed system, okay? So right now we haven't talked about a control volume. We need to convert the same expression for a control volume. So for a control volume, what's going to happen is that obviously the rate of change of energy, because this is the instantaneous rate, so it's going to be equal to obviously the heat content rate, so Q dot, minus W dot, plus additionally there's going to be some term here because now we're talking about a control volume, okay? And for a control volume, what we've seen is that besides just the energy changes that take place for a control volume, so let's just consider, let's say, okay, hold on, just let me represent it here. So let's say that we've got a control volume in the system here, and within this control volume, what we saw was that not only energy changes can take place, but also mass changes can take place too. So for a closed system, we only accounted for the energy changes. We haven't talked about the mass changes in this equation. So to include those mass changes, then obviously there would have to be some additional terms here, right, that would have to be included to represent the mass changes that are taking place. So like, for example, if when we say mass changes, what we mean is that there's going to be incoming mass and there's going to be outgoing or exiting mass. So we have to account for the energy changes that take place for the incoming mass plus or minus the energy changes that take place because of the outgoing mass. So because of the incoming mass, which is going to be, let's say if mass is incoming somewhere here, and I represent that mass flow rate by m dot I, then I would have an additional component in here which is going to be accounting for the rate of transfer of the internal energy, of the kinetic energy, of the potential energy, of this incoming mass, right? So this incoming mass, I need to account for its internal energy, which is, I'm just going to represent it by UI, plus I have to account for its kinetic energy, which is going to be Vi squared. This is the velocity, Vi squared divided by 2, plus GZI. Okay, so this entire thing basically represents the rate of transfer of energy of the incoming mass, of the incoming, let's say, fluid. If, let's say, some kind of fluid is entering into the system as a mass, some kind of fluid, so it would be rate of transfer of energy of the incoming stream of fluid, right? So that's what this entire term represents. Minus, so if let's say that this system, let's say, has an outgoing portion somewhere here. So then this entire thing is the control volume that is being represented. So when there's going to be an exit stream here, then the mass flow rate of that exit stream, I could represent it by m dot E. And now I have to account for basically the rate of transfer of the internal energy, kinetic energy, and potential energy of the exiting stream as well. So minus m dot E into the same thing, but obviously it would have to be the exiting stream's energy, the exiting fluid's energy. So plus this would be velocity of the exiting stream divided by 2 plus GZE. Okay, so this entire thing now accounts for the rate of transfer of energy of the incoming fluid minus rate of transfer of energy of the outgoing or the exiting stream of fluid as well. Okay, so right now we're talking about, let's say, a fluid that is entering into the system. This is one of the examples. Okay. What else do we need to account for? I could also, let me just show you here. This is called the control volume energy rate balance, the equation that we've seen over here. This one. This is called the control volume energy rate balance, and this is basically the conservation of energy principle in the form of an equation. Okay, so in the form of a statement, what you would be saying is that I could also write this, because this is the energy changes that are taking place across the system, and our system is called a control volume, so I could put the subscript CV over here. And this is just the conservation of energy principle. Time rate of change of energy that is contained within the control volume at time t is equal to the net rate of heat transfer energy at time t minus net rate of work transfer plus it would have to be net rate of energy transfer into the control volume that is accompanying the mass flow. So because that is the net rate, so net rate is going to be equal to the incoming rate minus the outgoing rate. Okay, so this entire equation is the conservation of energy principle. And if, just to have a check, if let's say our system did not have any mass flow in or out of the system, then these two terms would be 0, and our system would essentially be reduced to this equation. And that would be true because then only energy changes are taking place and mass changes are not taking place anymore. So that would be the equation for the closed system, and the schematic would represent the closed system in that case as well. So now that we have this equation for a control volume, I could also represent it in terms of, let's say, the system that is being shown here, that this is the control volume here, right? So let me just hold on. So this is our control volume, And what we're saying is that this incoming fluid element, okay, so right now we're talking about a fluid. This incoming fluid element, which would be incoming at a certain mass flow rate, would carry this energy within it when it's coming in. And the exiting mass flow would carry this energy when it would be leaving the control volume. But what we have not accounted for here is the work done contribution. So this is what we're going to look at next. That how do we account for this? Because when we're looking at this incoming, let's say, flow of the fluid, then there's an additional term that we need to account for, and that is what we're going to look at right now. So we're going to look at work for a controlled volume, and we can imagine it in this kind of way, where let's say this is just an imaginary piston here. So this is our control volume that we just saw, and this was the fluid element that we were looking at that had an initial mass flow rate m dot I. And now what we were saying was that this fluid carries within it a certain energy, but in order for this fluid to move into the control volume, obviously it's a non-fluid flowing fluid right now. In order for this fluid to be pushed into this control volume, there needs to be a certain force that needs to exist, right? Because nothing can move on its own. So in order for this fluid to move, there needs to be some kind of force, and that is the pressure force, basically. That is the pressure force because the fluid, the pressure that is within the fluid. So the pressure for a fluid is represented by force divided by area, right? So if I was to represent for this fluid pressure, which is being represented by P, I'm just going to represent it by small p actually. It's one and the same thing. And so for this fluid and the cross-sectional area that we're looking at over here, which is being represented by A, the force that would have to be applied on this fluid element to make it move into the control volume is going to be F. Okay, and this is the force that is being applied on the imaginary piston here. This is not a real piston. Obviously, what actually is happening is the pressure forces that are within the fluid are pushing this fluid into the control volume. But obviously that is because of the force. So the force is going to be equal to pressure into area, right? Just this relationship written in a different form. And now to push this entire fluid element into the control volume, this force has to act through some kind of distance, because that is what we said work is. That work is equal to force into distance in a way. So for this, obviously this is the force, and we're saying that, okay, so this force has to act through this distance L, and then the work done is going to be equal to, so the flow work, it's called flow work basically. So the work done is going to be equal to force into length, or I could write it in terms of pressure into area into length, and area into length is basically volume, so it's going to be equal to pressure into volume here. This is volume, not velocity, just remember that. And if I was to write it in terms of a per unit mass basis, then this work is going to be equal to small w here, and I'm calling this flow energy, so this is the work done across the fluid element by the fluid element, you could say, and it's going to be equal to P small v, because now we're talking about a per unit mass basis. So that means that we need to add this work into the system, because the equation that we previously saw, when in that equation we had this term minus w dot. This work then can, for our own convenience, we can separate it into two contributions. The first is basically the work that is associated with the fluid pressure as the mass is being introduced into the system at the inlet, or the mass is being removed at the exit. Okay, so that is the first one. And the second one, so the first contribution for this is going to be the flow work that we were talking about. And the second contribution for our convenience could be all the other types of work done. All the other work done effects, like if there's a rotating shaft, let's say within our control volume, or if there's some boundary that is being moved, so that's going to account for work done across the control volume, or if there is any electrical effects, that's going to come under work done across the control volume. So we can divide it into two, right, just to make it easier for our own understanding. So I could write then work done is equal to work done across the control volume, and plus that's going to be basically, so plus we would have to have flow work here. The flow work is in terms of the mass that is exited the system and mass that is incoming into the system. So the mass that is incoming into the system by that is going to be represented by a negative sign. And why is that? Because energy is being transferred into the control volume, right? So because the sign convention of work when energy is being transferred into the control volume, it's going to be negative. So it's going to be m dot I into basically pi into vi, which is small v here. We're talking about specific volume here. And plus, because this is the energy that is outgoing, so then obviously this is going to be preceded by a positive sign here. So it's going to be positive m dot E into PE into specific volume of the exiting stream. Okay, so this is what we have to account for. So what we're going to do is we're just going to, the equation that we saw previously, we're just going to substitute this into that equation. And once we do that, what we're going to have is, let me just see if I have it written down here. Right, so these are the two equations that we have now. This was the first equation that we previously worked out, and now this is the equation that we've just worked out. So this is, I'm just gonna, what I'm gonna do is I'm gonna plug all of this in here. When I do that, this is gonna be replaced by work done across the control volume, and because this is something that I can take a common factor off with this, so I can put this in straight here, and just like that I can do the same thing over here as well. The sign conventions are obviously going to change because this is minus w dot, so this is going to become this is going to have a negative sign next to it, this is going to have a negative sign next to it, this is going to be positive when it goes in there. So I'm going to be left with this equation here. So m dot I into ui plus pvi. And if we look at this entire term, this is actually what we've looked at already previously, that u plus pv is basically known as enthalpy. Right? So it's enthalpy over here, and I can replace it. And I can call this entire thing hi, and over here I can call this entire thing enthalpy of the exiting stream. So I can just reduce this equation into this form. What else can I do? Yeah, another thing that I would have to account for is that what if we have multiple inlets and we've got multiple outlets? So then we would have to have a summation sign in here, which would basically represent uh, all the incoming streams. So if there are several locations on the boundary through which mass is entering into the system, then you would have to account for that. If there's several locations on the boundary through which mass is exiting the control volume, then the summation sign is going to account for that as well. And basically I can just write this entire thing in this form. And this is called the energy rate balance. And this is accounting for, this is just accounting for the energy within the control volume. And what it says is that the rate of energy that is increasing or decreasing within the control volume is equal to the difference between the rates of energy transfer in and out across the boundary. Okay. So all we've done is we've just applied the same principles that we applied for a closed system, and we've extended it for a control volume now, which is also called an open system, right? Other than this, we need to look at a certain special case again when we talk about a steady state uh, system, a steady state, control volume at steady state. So I'm just going to look at it, look at this special case for it, which would be basically, this is, before I do that actually, I'm just going to look at this equation again, and I'm going to just write the steady state forms of the mass and the energy rate balance. So the mass one we already saw previously in the previous video, that for a steady state system it reduces to the conservation of mass equation basically reduces to this equation, right? And what else? We're actually just scratch that. I'm just gonna show you what it means over here. That when we're looking at the steady state form of the mass and energy rate balances, this is from the previous video that we saw. This is the steady state form of it. And when we're looking at the steady state form of the energy rate balance, the left side of the equation goes to 0, because on the left hand side, this is what we had, dE by dt, and this goes to 0 for a steady state systems, for a steady state control volume system. And we're left with this equation over here, or we can rearrange it, take this onto the other side, or take, let's say, work done onto the other side, the exit energy rate out onto the other side as well, and this is the equation that we are left with. Okay, so now we can move on and we can look at the special case when we've got only one inlet and one exit. And we're just looking at this because a lot of important applications related to thermodynamics involve only one inlet and one exit. So for a one inlet, one exit system, so let me just draw a schematic here first. So let's say that this is our system that has a single inlet, single outlet. This is our control volume within the system. And the mass, the conservation of mass equation basically reduces to m dot 1 is equal to m dot 2, because over here we've got m dot 1, and over here we've got m dot 2. And what we're saying is that at steady state, because mass flow rates are equal to each other, then the incoming mass is equal to the outgoing mass flow rate. So then this is what our equation is reduced to. M dot 1 is equal to m dot 2 for the system. And the energy rate balance, that is going to be reduced to this now, because m dot 1 is equal to m dot 2, or m dot I is equal to m dot E. So in the previous equation, we can just substitute, instead of m dot E, instead of m dot I, we can just substitute it by m dot. And then we're going to be taking this out as the common factor, and it's going to be multiplied with the change, or like the differences between enthalpy between kinetic energy, between potential energy. Or if you were looking at this um, divided by mass flow rate, then this is the form of equation that it's going to be reduced to. Now with this equation, this is an important equation that we're going to be looking at for different systems like let's say nozzles or diffusers or turbines, and we're going to see that this equation is the one that is applied to all those systems, because those systems act as control volume, because not only energy is being exchanged between the system and surroundings, but mass is also being changed, being interchanged or moved, because fluid is moving into or out of the nozzle, let's say, or fluid is moving into or out of the turbine. So with this equation, though, usually um, when we're looking at, let's say, this kind of system, because there are no rotating shafts in here, because there's no electrical effects that are taking place, so usually this term drops out. This is not always the case, but usually this is what happens. Other than this, this term, the potential energy term, this usually drops out too, because the elevation changes aren't really taking place to an extent where this would have an important effect. This is usually negligible, so this drops out as well. Besides this Q dot over here, if let's say the control volume is losing heat, so if you had a water heater, let's say, or a geyser, let's say, in your homes, then it would be losing heat, right? So then for that kind of system, Q dot is going to be negative. But if the control volume is really well insulated, which we assume in a lot of cases when we're looking at, so then that means our system is an adiabatic system, then Q dot in that case is going to be equal to 0 for an adiabatic case. What else? The enthalpy changes are probably the most important changes that we have to look at between the exit and the inlet states. So we use tables for that. For ideal gases, we approximate it by something that we already looked at. Delta H is equal to Cp into delta T. So for ideal gases, we use this relation. For fluids, usually, otherwise, we look at tables, thermodynamic tables. Kinetic energy changes, again, these could be neglected in some cases. In other cases, they're not neglected. So it depends on what kind of system we're looking at. And also, we have to account for the units over here, because this is going to be in meters square per second square, which is equivalent to joules per kilogram, right? So this is in meters square per second square. We have, and this is basically joules per kilogram. And usually what we've seen from the tables is that enthalpy is given in terms of kilojoules per kilogram. So you have to make sure that when you're using this relationship, you're converting this into kilojoules per kilogram. And you can do that just by dividing whatever term you get here by 1,000. So that's going to be in terms of kilojoules per kilogram. So when do you neglect this term, or when is it negligible? When you are looking at velocity changes that are extremely small. Because when velocity changes are extremely small, then that only corresponds to a kinetic energy change of, let's say, 1 kilojoules per kilogram at most. Or in a second case when you can neglect this term is when, let's say, the velocity isn't changing. The fluid stream that is entering in has the same velocity as the fluid stream that is outgoing here. So then that would be V1 is equal to V2. That's a special case again. So two ways in which we can neglect this kinetic energy term. The first one is when the velocity change is really small. Okay, so what I mean by that is that, let's say, if the velocity change was, let's say, 45 meters per second or less than that, then I could neglect this term. The second one is if V1 is, let's say, approximately equal to V2, then I could neglect this term as well. The potential energy term is mostly neglected because um, a potential energy change of 1 kilojoules per kilogram, what it means is that the elevation has to change. So Z2 minus Z1, elevation has to change by 102 meters. And that is a huge change. So usually in industrial devices, when you're looking at turbines, let's say, or compressors, the elevation doesn't change it this much at all. So the potential energy term is always neglected for those kind of devices. So the only time the potential energy term is not neglected is when we are looking at a process that is about pumping a fluid to higher elevations, and we want to see the required pumping power, let's say. That is the only time when you don't neglect it. Otherwise, you end up neglecting this term. Okay. So yeah, just go ahead and see different cases. Maybe go and take a look at nozzles. Let's say take a look at diffusers. Take a look at turbines. We're going to discuss that in the next video as well. But they're going to illustrate the use of this equation and this equation over here, because we're going to be looking at systems at steady state only. And when it comes to steady state systems, these two equations are what are valid for them.